is here, fly, stuff like that. So you just install. How is it installed? We can talk later. I want to this I may go through this presentation again tomorrow with the sense. Today we are going to focus only on material behavior. Okay, so you'll probably see this twice. So this is all, us installing and everything. This is how it works. I'll explain all of this yesterday. That's me. This is all us installing in the track and stuff. This is another site. That's me again installing, and this is the boring logs. Again, we're going to look at instrumentation stuff tomorrow, not today. This is all us installing and putting. That's again me trying to install. That's me collecting data. That's under the train, and blah blah blah. Okay, this is analysis of acquired data. So this is what I wanted to show: permanent deformation accumulation. Okay, look at this. So the way you want to understand this plot is every sensor gives the deformation of that layer only. How I'll do tomorrow. Okay, 1 is only ballast layer, 2 is only sub-ballast layer, 3 is only 5 ballast, 3 is sandy loam and stuff like that. Look at the permanent deformation. This is data collected over 550 days, which is 1.5 years, right? So I used to go. So this is where I used to be more of an Uber driver than a researcher, because my base was in Champaign, Illinois. The site was in Philadelphia, Pennsylvania. It's a 13-hour drive, and I got so used to it that I'll get up in the morning, 6 o'clock, start driving, reach there 7 o'clock at night, non-stop. Myself, nobody else, and then just collect data the next day and then come back and stuff. So anyway, look at this. With time, this is a track transition. This is a bridge approach. Remember I said how at bridge approaches don't compact very well because there is many challenges and stuff like that. Look at the permanent deformation. So this is LVDT1, which is the ballast, the top layer. Look what happens. What is going on here? Say again. They resurface the track. Like in railroad tracks, it's not an overlay or anything. It's called a tamping operation. It raises the track and it fills it with ballast and stuff. And when it raises the track, my sensor got lifted, right? So that's the negative. It goes up, and then again starts collapsing, right? So this was a 3-year, $1.6 million study that, my advisor was the PI, but I was the lead researcher on this one. And honestly, this project is the reason I have an academic career, because my PhD was very ordinary. I'll tell you from now very openly. I was not, my research in PhD was just okay, nothing standing out. But this project is what propelled us to the thing, is that because nobody had done this in the world, and we did this, and we actually identified that permanent deformation that you see in railroads, it's this much is coming from ballast. Everything else, look where they are standing, almost negligible. So it's your rocks that are rearranging and stuff to cause all the track defects and stuff. And there is a big problem with railroad, right? If a pavement has a big bump, you are interacting or hitting it with what? Tire. What is the tire? What is a rail? And what is it riding on? Steel. So a steel to steel bang is a lot worse than a rubber tire to an asphalt pavement bang, right? That's derailment risk and stuff. So that's what we found on investigating. So the project's name was investigating the root cause of what is known as differential settlement. The problem is very commonly known as bump at the end of the bridge. You probably have heard it. The way I explain it when I give talks related to this to students, I say, a friend of yours is driving and you are in the car closed. over a bridge, you always know, right? Because when they enter the bridge, there is a duck duck. When they get off the bridge, there is a duck duck. Where does the duck duck come from? It's differential settlement. There is always an elevation difference. Why does that happen? Because the bridge is standing on deep foundations. It's going to rock or something. It's not settling. And your approach is a fill layer or something, either an embankment or something like that, right? And that's going to settle with time. That's the permanent deformation. That's rutting, right? So that's what I wanted to show you is MDDs. We actually measured this. This is another site. Again, only after about 34 days or something, or 20 days, they resurfaced, and then they came back after about 360, 375 days, they resurfaced and stuff. Look how robust and resilient these instrumentations are. They actually stayed there irrespective of the maintenance and stuff, and they were giving us data and stuff. So this is transient. Sorry, this is permanent. What about transient? Transient is basically, I don't call it elastic, I call it transient, because I don't know if the transient is 100% plastic happening there. What I'm measuring is transient, like alive. So this is when I used to go sit down on the side of the track with my laptop and in an instrumentation van, and then we would collect data under train loading. This is individual trains passing, right? And as you can see, there is a big, there is this, the axes are the same. So look at here, it's, or the axis scale. So it's about 0.33, it's about 0.1617, about similar something. And then as you go down, it's much lower than that. That's obvious, right? As you go down, stress levels go down, so your deformations are going to go down and stuff. This is Acela Express. Basically, this is a type of train. It has 32 wheel axles, and this is, this is the beauty of instrumentation. You can actually take a look: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. That's 32 axles right there. You can count it. This is your load cell measurements, load measurements on the track as the wheels are going, right? And then you just, these are the track settlement trends. Why did that happen? This is GPR data. Does everybody know what GPR is, or anybody has heard of it? Sound penetrating radar. Okay, it's very commonly used to measure, in pavements, like pavement thicknesses. These days they can actually measure pavement layer densities using that. There are methods as well. In roads, it's very commonly used to study the quality of the ballast layer. If it is fouled, not moisture, no moisture and stuff like that, right? So this actually is GPR records. This is what is known as running roughness measurements, and there is a way to read this. The y-axis or the vertical axis is time. Okay, think of it as an increasing time. So it's 60 months. So 5 years of data here. What this means is red means it's a very rough track. Blue is best track, green and yellow slowly getting bad to red. So imagine this. So it was red. They came, fixed it. Then it became bad again. And then they came, fixed it. And then it became bad again and stuff. So this actually shows recurrent maintenance of the track. Okay. So we actually identified this location, and this is where we installed the sensors. And this, look, this is another location, but this is 60 feet. The previous one was 15 feet from the abutment. So very close to the abutment. So there is no compaction, there is no stabilization happening. It's very, there is some stress wave reflection happening and stuff. This is 60 feet. 60 feet is like what? 20 meters. It's far enough where they are not worried about resonance. They're stabilizing or whatever, however the material is. So look how less the permanent deformation is. It's not just stabilization, by the way. There is a lot of stress wave reflection happening, because when the trains are moving, the stress waves moving through the layers, right? They actually rebound from the abutment and they cause all sorts of havoc and stuff like that. That's basically that. Okay, then we did some remedial measures. We actually we went and fixed the ballast layer, and we again measured, right? Look here, so this is settlement of previously, and then we went and did some measurements, remedial measure. I'm skipping like crazy because I want to show no, I don't want that. I thought I had some. Okay, let's talk about this a little bit. This will be a good leeway to some discussions tomorrow and so on. Now we are talking about support conditions. As what did I say? Pavements and railroads are very similar as long as you are eliminating the train or rail and the tie and stuff. Underneath the tie, it's pavements. Same stuff. So now you can monitor support condition underneath the tie, which is basically a substructure assessment. So this is load cells. We'll go into a lot details tomorrow, but what you can actually see is let's go here. Let's go here. Take a look here. Wheel load 15 feet location. So the same train going, and we are measuring how much it is impacting the rail track. Okay, 15 feet location and 60 feet location away from the bridge, closer to the bridge. This is the equality line. Most of the points are here. What does that mean? What does this mean? This is an equality line, so it's on the bottom. So what does that mean? It's lower on the 60 foot, higher on this, right? Do you understand what I'm asking? X versus Y. If we have an equality line, if it's plotting below, X is greater than Y, right? That's what I'm saying. So what's happening here? On these tracks, on these locations, or because of this, on these dates, the 15 feet location has a higher wheel load than 60 feet. That's because there is a dent, there is an unsupported condition, it's banging it there. That's the problem. Something called missing ties and stuff. We'll get into a lot of this tomorrow. So then we use some GeoTrack, which is a modeling software, to model these. Again, mostly tomorrow, I think I will show this. This is, look, this is manual. There is no back calculation software for railroads. So this is back in 2013, 14 when I was doing this. This is the actual measurement that I just went and then just tried to do measured versus calculated. This is manual back, like you were doing yesterday. I was just manually changing values and stuff to match and then calculate. Yes. Very good question. There is actually, I think there is a number. I don't know that below. It's probably couple of 2-3 millimeters or something like that. I don't know. They don't really quantify it as a rutting. What they quantify it is called track irregularity and track surface profile differences, and there are specifications on that. But anything, even as epsilon value is bad, because you are talking about rail, steel on steel, right? So it's a very, very sensitive subject. So how much it degrades and stuff, and then you can actually back calculate the modulus values of the layers and stuff. Okay, one last thing I will show on this thing before we go into something else. This is some remedial measure we approached, and this is another thing called gluing of ballast we approached, and then we did something called under tie pads, and how that improved and stuff. I can show you this. So yeah, this is the team basically what we were doing over there. So I wanted to just give you a quick idea about how rutting or permanent deformation is important for railroads as well. One thing I skipped here, I just want to quickly say before we end up or before we stop or go into other things, is the same concept of constant confining pressure, variable confining pressure, like the moving wheel load, that becomes very significant in rutting. When you simulate moving wheel load, when you simulate rotation of stress paths, the material behaves very, very poorly in rutting. That's where you catch significantly. So even if in resilient modulus it's not simulated in a testing, it's very important to do it in permanent deformation. And this is some of the works that at University of Nottingham they did different PQ stress paths. This is A, this is B, C is this called constant one. C is basically what your standard testing applies, and D, E and stuff, you can actually change stress paths, and then you can have significantly higher permanent shear strengths and stuff. This is some P and Q for in actual airfield measurements. These anything below is extension states, anything above is compression states. Remember, in our traditional testing, we always stay in the compression zone. We never go into extension. But real data is showing that your actual material is exposed to a lot of extension because of the moving wheel load and stuff. So that's the reason it's very important to stay there. And these are like different stress paths. It's not possible to go over all of these. This is some test that was developed. We don't have time for all of this. Single path, multiple path. As you do a single stress path testing, your permanent strain is going to be, this is permanent vertical strain, this is deviatoric strain, and this is volumetric strain. You actually see changing. Both volumetric and deviatoric strains change when you study multiple stress paths. There are some test methods. We're not going to go into those details. Changing stress paths to study permanent deformation. Okay, that's pretty much it in terms of what I wanted to cover under repeated loading. So we still have about 14 minutes. So let me recap a few things. So most important behavior is repeated loading behavior for aggregates, unbound materials, right? Because they are loaded under repeated loading. Resilient modulus and permanent deformation. One is kind of an elastic response after some initial settlement. The other one is that settlement part, right? The resilient modulus is recoverable, so you can predict it from different properties. It is stress dependent, is material dependent, yes, and whatever. But the plastic deformation is not something that you should only look at elastic response to predict. You should look at strength to do that. So your strength of the material is very, very important when you look at permanent deformation. So when all of you running resilient modulus test, you can get by without running a shear strength test. But if you are doing any study on rutting, like you are doing study on shake, shear strength test is a must, because otherwise you have no idea what your stress states are with respect to the strength of the material. You have to quantify it as a percentage, saying that this is the percentage where I was and that is what it is. Because the first question anybody will ask when you're doing rutting study is, what's the strength? At what level of the strength are you loading it? Because that's very, very important. Then we talked about the models and stuff. Resilient modulus, we talked about different models, how to fit the model, what the models mean and what not. Why is that important? Is because that gives you an idea to take any stress state of predict a modulus for that material by using the model. Otherwise, you cannot just, no, you cannot have an idea of about the modulus of a layer because it's stress dependent. It's not a constant number, right? So then the question becomes, how would you take care of stress dependency in a layered elastic formulation or something? Just use sublayers. Just use sublayers, find representative modulus values or find representative stress and then iterate on that. I think I told you this. So last thing I will say, we said this a little bit yesterday, but you are like, okay, how now I have sublayered, I have this layer, I'm going to sublayer this. Okay, and you are saying, okay, how am I going to now assign modulus values for all of them? Right? What I would say is assign, let's just say to start with, assign a value of say 30,000, right? And then apply a load, run your layered elastic analysis, learn your IIT PAVE or whatever you're trying to do. At this point, at this midpoint, find your sigma D, sigma C, or basically sigma 1, sigma 2, sigma 3 essentially. Sigma 1, sigma 2, sigma 3, find all three of them, right? Then using that, calculate theta. Then using k theta model, calculate MR. Then compare this MR to this 30,000 that you assumed. Are you close? If you are not, take an average of these two numbers, rerun the analysis. Take an average, let's just say this is 20,000. So the average of 20 and 30 is 25. So in your iteration number 2, make it 25,000. Run the whole analysis again. Then check. Once you are close enough, you're like, okay, this is my converged modulus. Now I am confident that for this layer, I can allow this, I can assign modulus and still be okay. I'm good, no problem. This you can do for thick layers. When you have 24 inches of aggregates, don't just assign one value, subdivide it, run some analysis and figure this out, how this is going to go. Which model is better? Is K theta model better, Uzan model better, ABP? Really no, pretty much anything will work. As you saw in your R squares, all of them gave very good R squares, I'm pretty sure, right? All the models will give pretty decent thing. Different purposes are more valuable when you are going to go do real extreme sensitivity analysis. But that's your way to iterate and stuff. Okay. For the tutorial today, what we are going to do is I'm going to start with showing some DCP data, some analysis of DCP data, how it is done and stuff. But I don't plan on spending more than say 20 minutes on that one. Okay, and then we'll go into I'll share ILIPAVE with you all, and then there is a small installation. You can install it, and we can actually look at ILIPAVE, what it does, what the software is, and you can have it. It's a research code. You can have it in your toolkit, and you can just run it anytime you want to do. It's a very, very quick run. You can have some ideas how the materials behave, what kind of things you can get, what is stress dependency, what is resilient modulus variation within layer and stuff like that, right? How many of you, again, masters and PhD students, or at least PhD students, I think I know the answer. How many of you have not been at all exposed to finite element modeling ever? Like, or you haven't even heard the name in a class or anything? Please be honest. 1, 2, 3, 4, 5, 6. Okay. All right. So let me teach you. This is my crash short course on what is finite element modeling. I have this way of teaching, which I like. That's since I learned it. There is a circle. Okay. I want you to tell me the circumference of that circle. How will you do that? 2 pi r. That's okay. 2 pi r. You're not allowed to do 2 pi r. The only tool I give you is this marker. What do? You put it here, then you rotate it here, then you rotate it here. How many times? Maybe 8, 9 times. Multiply by the length of the marker. Good? What did you just do? You somehow discretized the circumference, but is it an accurate measurement? You missed all of these curves, right? Now I'm going to break this to 2. Because they're going to cut my. Yeah. But if I break this into 2, what will happen to your measurement? More accurate? Now I give you only the cap. More accurate, right? That's finite element modeling. You are discretizing a system into little elements. You are studying a very little element. You are trying to then assemble the entire thing together. That's what it is, right? Does that mean when I have a pavement for you or something, and now you are trying to and I have a crack over here or a slab over here, joint, and you're like, man, my layered elastic theory is not going to work because it's going to talk about semi-infinite elastic space and stuff like that. What am I going to do, right? You're like, okay, let's not worry about it. We're going to talk about very small elements, and when we come here, we're going to change some properties here and whatnot to capture that. Other than that, everywhere else it's going to be the same, and I'm going to assemble the entire system together, right? Then make an inference about this. So finite element modeling is a numerical method. It's not an analytic method. It's not 2 pi r. 2 pi r is analytical, right? PL cube over 48 EI is analytical. Have a solution to it. Numerical methods are you're discretizing it, you're studying something, you're trying to generalize it. So the best, an ideal condition, the best finite element method is what matches the analytical method for an ideal thing, right? For certain cases, analytical methods don't exist, right? He threw me this 2 pi r thing in a second. Now I'm going to do this and then give him this. Then his method is going to collapse. Then 2 pi r anymore, right? But your method is not going to collapse because your cap you can still measure. Right? So in pavements, now let's go. What do you talk? Layered elastic theory. There is a very common analysis thing called homogeneous isotropic semi-infinite elastic half space. Okay, what is elastic? You all know. What is